In this section, we're going to look at the simple calculations to determine how quickly a gas will diffuse or effuse. Quick reminder here, diffusion is simply the mixing of two gases. Effusion is the escaping of a gas out of a container. So when we talk about this, we're going to talk about effusion rates, but we can make some comparisons in terms of diffusion and how quickly they'll mix. So to do that, the concept is called Graham's law. Graham's law basically talks about how quickly gases will mix based on three things: mass, velocity, and molar mass. They're all tied together. The simple concept of kinetic energy, which comes from physics, uh, calculation for kinetic energy is equal to 1/2 times the mass of an object times its velocity squared. What Graham's law did is basically modify this equation. So what it says here, the velocity of gases are inversely proportional to the square roots of their molar masses. So here's what I do, two things here. The velocity of gases is dependent upon molar masses, more specifically, the square root of their molar masses. But here's the more important piece: inversely proportional. So that's what it means. If velocities go up, that must mean molar masses go down. Lighter, if molar masses drop, speeds go up. If the molar mass of the gases go up, the speeds go down. Pretty simple concept there. So what does that tell us? Heavier gases move slower, lighter gases move faster. So we can keep that straight. Calculations are easy. So we take the kinetic energy equation and simply modify it. And what we end up getting is a proportion or a ratio. This is not an actual velocity, meters per second, feet per second, miles per hour, but it's a rate. It's a comparison or ratio. So what we have here, the rate of gas A compared to the rate of gas B is equal to the square roots of their molar masses, and again, the inverse of those molar masses. Okay, we see that they're flipped. We also simply can do, again, since we're just comparing the rates as a ratio, the density of gas B over the density of gas A. Again, square roots. This is not an actual velocity or an actual speed, but it's just comparing them. A compared to B. So we might get an answer of 4.1. What does that mean? That simply means is A is 4.1 times faster. If we do this calculation and A over B ends up being 0.8, that means A is 0.8 times faster, which actually means A is slower than B. All right, so that's what we're looking for. So on sample problem on page 388, you just look at a calculation between hydrogen and oxygen. So we're talking about what is the rate of hydrogen gas compared to oxygen. So the rate of hydrogen over the rate of oxygen is equal to the square root of 32 over 2. Now, what does that mean? That means when we solve for this, the square root of 32 over 2, when we solve this problem, we are going to get what the rate of hydrogen is compared to oxygen. So you can see in that sample problem how they solved that. So when you get an answer, again, I want you to read that description so that you understand what that number is. Okay, and again, I'm not going to put that number here. First of all, I want you to think about square roots. And again, you can look in your book to double check that, but I want you to revisit that a little bit. Okay? So, pretty simple concept there. Now, what I want you to do, I got two show me's here. I want you to do practice problems number 1 through 3 on page 388. The hardest part here is, what does the answer mean? Okay, so you do the calculation, and you've got to keep it straight to say, okay, well, the answer is this. It means then gas A is 2 times faster, or 4 times faster, or half as fast, or a third as fast. Calculation is very simple, but again, we need to be able to understand once we've done that easy calculation what our answer is telling us. Sometimes that's the hardest piece. Okay, so pretty short section there. Should be able to do some of those problems and be done with it then.